In episode 47 of the SOC Level 2 training series, we are going to go through the anti-reverse engineering room, which is a part of the malware analysis module inside of the SOC Level 2 pathway of TryHackMe. And this is the second to last video that is going to be, or at least for now, that will be inside of the SOC Level 2 playlist, because we are just about to wrap up malware analysis, and we're essentially going to be done after we do that. So I'm very, very excited about this. Reverse engineering is one of those things that we do as security professionals, as security engineers, security analysts, when we go through looking at malware and trying to reverse engineer, trying to backtrack and kind of see what the malware is supposed to do. And then there is anti-reverse engineering, which is what the hacker does, what the attacker does to prevent us from being able to reverse engineer, right? From being able to see the things that they're intending for their malware to do. So what they are going to do is anti-reverse engineering techniques, and then that's the malware author's job, and our job is to notice this and then get around this. And so the concept here, or the overview, excuse me, is we have the intro, obviously, anti-debugging, and so we did debugging in the last video, and we're going to talk about anti-debugging using Suspend Thread, the VM detection, virtual machine detection, and then virtual machine detection by checking the temperature, packers, and identifying and unpacking. And then we have the conclusion, and we're going to wrap it up for this video, and you will be dismissed. So very, very excited about this specific one. Our creator for this is a rebel. That is the user or the developer that developed this room for us to be able to use. This is somebody on the staff of TryHackMe. Obviously, they're based out of the UK. They're based out of Great Britain, the United Kingdom. There we go. And so they've done a lot of great stuff, and their rooms that they have created is also pretty extensive. So they've created a lot of rooms that we can use. So shout out to a rebel from TryHackMe. Very, very grateful for you doing everything that you've done for us so that we can learn and develop our skill sets. If you're serious about your CySec education and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the supporter, agent, guardian, and master. Each tier gets their own Discord server and early access to content. The agent, guardian, and master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. Now, without further ado, let us jump into anti-reverse engineering. Our job as security professionals, and a lot of times, is going to be reverse engineering, which is the process of studying a technology product or a software or hardware, learning how it works, and extracting the functionality or this design information. Basically, when you do engineering is when you build something. Reverse engineering is trying to see how that thing actually works by kind of breaking it down into its parts, right? And so the same thing applies to malware. When we do reverse engineering against malware, we're trying to see how the malware was engineered, how it works. And malware authors, the people who created these things, are trying everything they possibly can to prevent us from figuring out their tricks and figuring out what their malware is trying to do, so on and so forth. So they deploy anti-reverse engineering tactics as they developed their malware. And that's the whole concept behind this specific video, is what is it that they do, what are the tactics that they do for anti-reverse engineering, and then how can we bypass those tactics so that we can actually figure out what the malware is trying to do. And that's the whole goal here. And this is the closest thing that we will get to advanced dynamic analysis, because this is technically a part of dynamic analysis of malware. So in this particular room, in this video, we're going to go through the various reverse engineering techniques that malware uses. And this includes virtual machine detection. So if a virtual machine is something that we would do, or what we would use as an isolated environment when we run the malware, so that it doesn't infect the rest of our computer. It only infects the virtual machine, and then we can just crash the virtual machine, right? And then we don't have to worry about the rest of our computer, and then we can just restart the virtual machine to try to analyze a different piece of malware. So virtual machine counts as a sandbox type of an environment, and that is something that a malware author is trying to detect. So they will try to detect whether or not their malware is being run inside of a sandbox or inside of a virtual machine. And if it is being run inside of the virtual machine, then it shouldn't do its malicious activities, because that would give us a clue as to what it is they're trying to do. Another way to do this is to obfuscate using packers, and we'll talk about this when we actually go into it. But packers essentially, or packing malware, is essentially disguising the various elements of the malware so that we can't see it with the naked eye when we do static analysis, and therefore we don't know what it's actually intending to do. And then there's debugging, which is what we did in the last video, where we ran through the malware activity step by step, literally line by line inside of the code. And we were like, oh, okay, this line does this and this line does this. And so that's called the debugging process. And they do this inside of software development in general. When you debug something, you go through the software line by line to see what each element of the code does. And then from there, if there is a bug inside of the software, then you can find out exactly what line that bug starts at and what the problem is, so you can fix it. So there is anti-debugging that is done for malware, because they don't want us to debug their malware. Malware is technically malicious software, so we can run the same type of strategies to debug malware, and an anti-debugging means that they don't want us to be able to do that. So the objectives are to learn why malware authors use anti-reverse engineering techniques, learn about the different anti-reverse engineering techniques, learn the techniques on how to circumvent anti-reverse engineering using various tools, and how anti-reverse engineering techniques are implemented by reading the source code. It's good to know basic and advanced dynamic analysis. So these are the things that we've done already inside of this module. So the last series of videos, you should already see, the debugger, reading assembly code, patching, all of those things have been covered in the last series of videos inside malware analysis. Basic knowledge of assembly, what it actually is, what it does, what it means, and the understanding of C programming concepts like conditions, like if-else statements, and the flow of a program. You don't need to know advanced C programming, it's just understanding what it is. And my recommendation is, if you don't know C programming code, one of the things that you can leverage is an AI tool. So Gemini, Meta AI, ChatGPT, Claude AI, whatever your favorite AI tool is, you can use one of those tools to go ahead and analyze code, and then it'll tell you, okay, this code does this, or this is what it's trying to do. So those are some of the tools and some of the prerequisites. And then of course we have a virtual machine that has been assigned to us that I've already started. And this virtual machine is a Flare VM. So Flare VM is a Windows-based operating system that is designed for malware analysis specifically. It comes pre-installed with a bunch of different tools that you can use to analyze malware either statically or dynamically. Statically means without running the malware. Dynamically means you actually run the malware and then you try to see what it's doing. So now that we have gotten all of that out of the way, let us go ahead and look at anti-debugging. As I mentioned already, debugging is essentially the concept of looking at software line by line to try to see which line of code is where the bug is, right? So if a software has a bug, that means it's not running properly. And if that is indeed the case, then we're trying to find out exactly what part of the source code that bug exists in. And so the same thing applies to malware. So when we're analyzing malware, we're trying to essentially find out where that bug is, especially if the malware is not doing what it should be doing. Meaning, if it's detecting that we're in a virtual machine, it's going to stop running the way that it should be running, and it's not going to do all of the malicious activities that it was designed to do, which means if it's not doing what it was designed to do, it has a bug in it. So we need to debug it. Now, that whole process is what we do as security engineers. Now, the malware author, the person who created the malware, is going to deploy anti-debugging techniques so that we can't debug their malware. Now, these are some of the commonly used debuggers, and we use the x64 DBG. In the last video, there's Oli DBG, there's IdaPro, and then of course there's Ghidra, and then we also have used Ghidra before as well. And the techniques are as such. So checking for the presence of a debugger. So the malware code looks for processes or files associated with debugging tools or hardware-based techniques like detecting hardware breakpoints. For example, a common anti-debugging technique uses the API function is debugger present to check to see if a debugger is running. And then that basically is what we did in advanced dynamic analysis. And so if the debugger is present, then the malware isn't going to do what it's supposed to do. Tampering with the debug register. So malware may try to modify or corrupt the debug logs, which debuggers use to control the execution of the code, which prevents the debugger from functioning correctly. So if the debugger is present, one of the ways that the malware can mess with it is to just modify the debug logs so that the debugger can't actually do what it's supposed to do. And then using self-modifying code, which is sophisticated, where the malware modifies itself while it's running, making it difficult for a debugger to follow the code flow. So those are very, very interesting series of tactics. This last one specifically because it's like AI basically. The malware is looking at conditional statements, right? So if a debugger is running, do this series of things instead of you doing what the other things are supposed to do, and it modifies itself while it's actually running, which is kind of crazy. So we're going to look at anti-debugging techniques in the next session. What is the name of the Windows API function used in common anti-debugging techniques? And that was the one that said, is debugger present? So let me make sure my keyboard wakes up. So is debugger present is the name of the Windows API function. So now let's look at anti-debugging using Suspend Thread, which we actually touched on in the last video. Suspend Thread is a Windows API function that's actually legitimate. It's a real function that's used to pause the execution of a thread in a running process. And you, again, can use this legitimately, right? But it's also something that can be used by malware to suspend any threads attempting to debug or analyze it. And that's one of the big things that it can do to just make the debugger not work, right? So if you can just stop the debugger from working, what better way is there to actually do this to get past the debugger, right? So the program that does this specific technique exists in our Flare VM. So you can run the 32DBG tool, which then you can run the opening the suspend thread executable, and then press F9 twice to continue the execution of the malware. And then x64dbg will now become unresponsive, and you can confirm the suspended process by opening the task manager, and then you can see that the process's status would be suspended. So we can actually run that, and then we can completely terminate it by doing end task to terminate the x64dbg. The code snippet below shows how the malware works under the hood. So this is our code snippet, and this is, I believe, the C language code. So I'm not that great at C, so I'm not going to even pretend to understand what this is. So what I'm going to do is I'm just going to copy this whole thing, because this is actually a very large piece of code. So I'm going to copy this whole thing, and I'm going to ask Gemini to give us a quick little high-level description of what it's supposed to do. Okay, so first there's a global variable, the D word, this element right here at the very, very beginning. This global variable is used to store the process ID of a detected debugger process, and it's initialized to -1 to indicate no debugger has been found yet. So that's what it starts at, and then if it is found, then this value changes. So our D word is going to be the global variable. And then we have the enumerate Windows processes, the callback function. And this is a callback that will be called by enum Windows for each top-level window on the desktop. Its job is to check to see if any of these windows belong to a process with a title that suggests it's a debugger. And then it will get the process ID, so it gets the process ID associated with the current window. And if that process ID, so it'll check to see if the window process or the window belongs to a specific process ID that enum Windows was called, which in this case will be the pre-ID of the potential debugger. and then it'll check the title of the windows as well. So get window text length and get window text W, all of these elements right here, this line of code right here, retrieves the title of the window. W suffix indicates wide character Unicode functions. If, so this is our first conditional right here. So the core detection mechanism, it checks if the window title contains the substring DBG in it or debugger in it, case sensitive due to the WCS STR. This is a very common, albeit easily passable way to detect debuggers like OllyDBG, WinDBG, etc., which have a debugger or DBG in their actual window titles and their names. If the match is found, the process ID is set to the PID of the detected debugger, and false is returned, which stops the enumeration of windows. Mallocation, dynamically allocates memory for the window title. It's crucial to remember that free this memory to prevent leaks, which is not done in specific function. This is a potential memory leak. Is the debugger process function takes the process ID as an input and use the enum windows to iterate through all top level windows, calling enum windows process for each one. And then this is the Windows API call that initiates the window enumeration, passing the process ID as a parameter to the callback. And then this return function right here, it checks if the debugger process ID that we had, which would have been set by enum windows processes, if the debugger window was found for that PID, it matches the input of DW process ID. So this is going to check to see if that global variable matches the input variable. Suspend debugger thread function. So the purpose is to anti-debug, right? So it enumerates all the running threads and attempts to suspend any thread belonging to a detected debugger process. So this is where that suspend thread element comes in, and it creates a snapshot of all threads running on the system, then iterates through all those threads inside of the snapshot, opens a handle to each thread with permissions to query its information and suspend or resume it. It gets the PID of the process to which the current thread belongs to, calls the previously defined isDebugger process function to check if the process owning the current thread is a detected debugger, prints a message if the debugger is found, so debugger found with PID, etc., suspending. And then this is the critical anti-debugging function, this piece right here, the D word that we went and looked at the very beginning, the global variable. If a debugger is found, it attempts to suspend the debugger's thread. Suspending a debugger's main thread can cause it to hang, become unresponsive, or crash, making it difficult for an analyst to continue debugging the malware. Used to print the last error, closes the handle to prevent, and then the main function calls the anti-debugging function and basically just kind of runs the overall debugger, right? So this is a full script that has multiple functions inside of it. It'll enumerate the Windows processes. It'll look to see if the debugger process, if it has the word debugger or DBG or anything in it, or if the PID matches anything. And then if it does, it'll actually suspend that thread. And then finally, just like many other script syntaxes or many other script processes formats, we always create a main function at the very end that will just call on all of the previous functions. So that is what this chunk of code does. And so now we have a description right here. So if you don't want to be bothered with reading the source code, here's the short explanation, which is basically what we just actually looked at. So it can effectively stop analysis from continuing the investigation. So fortunately, we have a way of dealing with this. Patching is one of the most critical skills required. And this is basically when we patch the software, right? So when you patch a software, you're fixing its debug, or if you're fixing its bug, excuse me. So we've already talked about this. So if there's an element of the source code that detects us using a debugger and then it stops running, we need to patch that element so that we can actually run the software. We can run the malware. So we want to patch the function suspend thread so that the debugger won't get suspended. And we open this by double clicking on the icon, press F3 to show the open dialog window, look for the sample file called suspend thread, etc. Press the F9 key to jump execution to the entry point as shown below. Right click anywhere on the main screen, highlight search for current module, then search intermodular calls. on the search field at the bottom, type suspend thread. This will filter the list, and then it'll show us the element itself, the suspend thread portion. And then now at the part of the code calls the suspend thread API. To skip the function, right click on the suspend thread line and select binary filled with non-operating protocols or non-operating procedures. Don't change anything, just press OK. And so what happens is that it'll replace that chunk with NOP elements that will stop it from running. So previously, the piece that was suspending a thread will now be replaced with non-operational chunks. And then this is what happens, and press 9 to continue execution, and we'll see that the debugger continues at the very end without crashing our debugger. While the console prints out the lines debugger found with PID suspending, it's not actually doing anything because we've skipped the function that does the suspending. And so this is great. However, if you try debugging again, you'll discover that it will start crashing again because our patches are reset and now gone. To avoid reapplying patches, we can export and import the patches for future use. So stop the debugging by pressing Alt F2, go through the patching steps in the previous section, but do not do the last step. So once the patches that you want are in place, you go to the top bar, click View Patch File to open the patch dialog window. The list of the patches will appear in the right panel, and then we can see that there are 6 entries to replace this one element, and this refers to the 6 memory locations, the NOPs. We're going to click on Export and then basically save the file, then stop the debugger and debug the file again. Because debugging has restarted, the previous patches have now been erased. We can restore it by importing the file that we made. So go to the View Patch File. By this time, press the Import button, and then you'll be able to import the previous patch, and then press F9 to continue it. So exporting and importing are very helpful in reverse engineering, as it allows to save your work, to save the hassle of doing them all over again. And then we're going to look at it in the next section, where we can do another reverse engineering technique and other ways to circumvent them. So what is the Windows API function that enumerates windows on the screen so that the malware can check the window name? And that was the API function that we had right here. I think it's called enum windows. Its job is to check if any of these windows belong to a process that the process title that suggests it's a debugger. Yeah, so it's enum windows that has that element. What is the hex value of a non-operational instruction, which is that 90 that we see right here? So if we go up here, right here, you see that these are all NOPs, so the hex value is 90. And if we also look at the source code that was changed right here, you can also see the hex values are all 90. So that would be the value. And what is the instruction found at memory location 004011CB? So let me see if it exists over here in our screenshots. If not, we actually have to run the whole thing. So CB, oh, it's right here. Literally, the instruction is add ESP, 8. That's the memory instruction. So we actually have that. So I was able to answer all of these things, ESP, 8. I was able to get all of these answers by looking at the screenshots. But basically, if you wanted to run this, if you have access to this virtual machine, because it is subscriber only for the TryHackMe users, if you wanted to run this, you would basically just do everything that we just did, right? So the very first time was to just open the debug tool, open the suspend thread executable, and then F9 twice to continue the execution of it. And then you'll see that it's suspended. You'll see that the debugger tool is suspended because the malware detected it, therefore it stopped it. And this is the code that we just saw that would actually do those things. And it calls enum windows to detect the DBG in the title, because that's literally what it's called, right? It has DBG inside the title. And so because of that, it does what it's supposed to do. So what we're going to do is what we would do is to patch it. So then you would open the debugger again, open the suspend thread executable again, and run it. And it'll jump to the execution entry point, as we just see right here. And so you can see it calls suspend thread, right? So that's the element that you run, but you don't run it twice, right? So this is the piece right here where it says press F9 twice to continue the execution. And in this particular case, you're only going to press it once because we want to jump to the location that the suspend thread call is made. And so this is the element where we're going to replace it, right? So you will right click. So right click anywhere on the main screen, highlight search for current module, then select intermodular calls, and then type suspend thread to actually find it, which is this piece right here, and then we'll be able to find that call function that actually is calling on the suspend thread. And then we can now be on that actual element that has the call to the suspend thread API. And then so what we're going to do is right click on it. So we're going to right click essentially on that line right there, right? Or right click on this element right here. And then you're going to go to binary filled with NOPs, don't change anything, etc. So why don't I actually do this? Instead of just doing the explanation, I'm just going to run it. And then instead of doing F9 twice, I'm only going to click F9 once. So we'll do file. We're going to open the suspend thread executable, and then we're going to run it. So let's go to the desktop. We're going to open up malware, and then we're going to add the suspend thread executable. And there it is. So now we're here. So now we can just do F9 is basically another way of saying we'll press this run button right here, and then you can also press the step into to get to the next element. So if I press run, it'll run, and then it immediately, that's the equivalent of doing F9. So this is the button that I ran. Because I'm using a virtual machine, I feel like F9 might not work, so I just pressed this run button. So it'll go to the first spot right here, this piece where you actually see suspend thread. And this is the piece that we're trying to fill with the NOPs, right? So click on this, and automatically I can just do binary fill with NOPs, and then that's it. So it's kind of, they gave us a few extra steps right here, but I can just right click on that and fill with NOPs, right? And then so what would happen ideally is that the next element should be replaced with NOPs. Now, we can see right here that 4011B1 is not the piece that I'm on. So I think I shouldn't be filling that piece with NOPs. So maybe I should be actually following the instructions that they're talking about. So it says search for current module and then select intermodular. So we'll right click, and then we will do search for, so this is at the bottom right here, and then we're going to do current module, and then we're going to do intermodular calls. So this is where it is, right? So search for current module, intermodular calls. We're going to do that. And then we get a chance to search through these elements right here. On the search field at the bottom, which is right here, we're going to type suspend thread. And there it is. So that, not threat, thread. There you go. So there it is. So now I have the suspend thread that's pulled up. And then from here, we can go ahead and right click on this function and then do the binary fill in. Or actually, no, it says skip this, right click on it, select binary fill with whatever. So, I mean, I think I see it, but it says, so maybe I need to double click on this and it'll take me to that element. Okay, there you go. Okay, there you go. Now we're at the place that if I replace it, it'll actually show me the same thing. 411B1 would be the next step right here, and I see right here 4011B1. So this is actually the element that we want to fill with NOPs. So we'll do binary fill with NOPs and then click OK, and now it'll fill that with these non-operating elements, right? So boom, now we have it 411AB to 411B0. So 411, there you go, AB to 411B0. It's all been filled in, and now we have the next step, etc. So now it says to continue the execution. So I'm gonna press continue and continue again, right? So run it. Show it to me, buddy. Let's see how it works. Do we have it in the background? Oh, there you go. It's actually running. So it's running in the background, debugger found with da-da-da-da, but it's not actually suspending anything, because if I go to the task manager, X32 right here is not suspended, right? So it's actually detecting what it's supposed to do. And then the exporting element of it was just something you can go review those things. I'm not going to export the patches because we're going to move on to a different element. But that was it. That was essentially us running through the instructions just so we can kind of see how the whole thing plays out. And you just saw that. So now we can move on to the next part, which is the virtual machine detection. Okay, so in case you don't know what a virtual machine is, it's basically a computer that you can run virtually, right? So it's a software version of the computer itself. You can run it on top of your actual current host, meaning you can have used something like VMware or you can have something like VirtualBox, right? And then you can get an ISO image, which is basically the image of the operating system that you can then run from your current computer, and it will act as a separate computer on top of your actual computer. So it's essentially another computer that's running. And so when you open up the malware inside of the virtual machine, it's not going to infect the rest of your computer because it's running in its own isolated environment. This is also known as a sandbox. So when we do this, this is the approach, this is the strategy to try to have an isolated environment within which we can actually run the malware so it doesn't affect the rest of the stuff. Now, technically, what I'm on right here, this piece right here, this is also a virtual machine that is now being hosted on my browser, and it is originally installed on the TryHackMe servers, and so I'm just launching that instance from TryHackMe, and now I have this virtual machine running, and so I can run a malware on this virtual machine and it won't affect my actual computer. So that's kind of the one of the big draws of virtual machines, especially when we're talking about malware analysis, dynamic malware analysis, right? So when malware identifies that it's running inside of a virtual machine, it can respond differently, meaning it can choose not to do its malicious activity. So it can execute only a minimal subset of its original functionality. It can self-destruct and delete itself or overwrite parts of its code. It can cause damage to the system by deleting or encrypting files, meaning the virtual machine itself, or just not run, right? So this is kind of probably the most clever thing that can happen, because any of these other things, either this one or this one, these are the best things that the malware can do, because if it self-destructs, then we're like, oh, it's definitely malware. If it causes damage to the system, we're like, oh, it's definitely malware. So these are the two things that if you're a malware author, you kind of want to do those, because you don't want to give away that you had the malware. Because if I am aware, if you self-destruct or if you cause damage to my virtual machine, then I'm like, oh, so definitely it was malware. Now we need to take even a more careful approach to everything that we're doing. But if it doesn't run, or if it's doing a basic subset of its functionality, then we're like, oh, maybe it isn't malware. We got to like dig a little bit deeper, but we still don't have our guards all the way up. I mean, we should at the very beginning of this because we suspect that it's malware, but you're not as on high alert as if the self-destruction takes place or there's damage taking place. So these are some of the techniques that it can the malware can run to see if it's inside of a virtual machine. So it'll check running processes, very similar to what we did for the anti-debugger, right? So VMs have easily identifiable processes. So VMware, for example, runs a process called VM tools, and VirtualBox has VBox service. And the malware can use enum process, the way that we did, to call all the processes that are running on the machine and then look for those names, right? It can check installed software. So it can look at the Windows registry, the software, Microsoft Windows current version, uninstall registry key, and then from here it can check the installed programs like debuggers, decompilers, forensic tools, etc. Network fingerprinting. It can look for specific MAC and network addresses unique to virtual machines. For example, VMs auto-generate MAC addresses that start with any of these number sets right here. So these numbers are unique and are specifically designed to a VM vendor called the organizationally unique identifier. So if the MAC address has any of these things as the starting point, you can rest assured that it's a virtual machine. Checking the machine resources, so we can look at a machine's resources like the RAM and the CPU utilization, and a machine with RAM amounting to less than 8 gigabytes indicates a virtual machine, because pretty much all laptops and computers these days especially start at a bare minimum of 8 gigabytes. I think now it's like probably even 16 gigabytes is like the bare minimum. So all of those things indicate it's a virtual machine, as they are typically not assigned to a significant amount. Like a virtual machine typically gets, let's say, 4 gigabytes of RAM or something like that. And then detecting peripherals. So the malware can check for connected printers, because it's rarely configured properly on VMs and sometimes not even configured at all, which is really not that big of a deal because I don't have a printer configured on my laptop right now. So that doesn't necessarily mean I'm on a virtual machine. Checking for domain membership. So corporate networks are usually target for malware, so it can determine whether or not we're on a corporate network by checking if the current machine is part of an Active Directory domain, and it can quickly be done by using logon server or computer name as an API call to get the environment variables. Then we can look at the timing of the base account. So it can measure the time that it takes to execute specific instructions or access particular machine resources. So some instructions can be faster on a physical machine compared to a virtual machine. So these are not foolproof techniques, but it's not uncommon to see malware using a combination of one or more of these things just to verify whether or not it's actually on a virtual machine. And to prevent malware from using some of these techniques, we can apply several changes to the system that will remove VM-related artifacts, like making the virtual machine look less like a virtual machine. Meaning we can remove or modify registry entries that the malware checks for installed programs, to hide the debugger, change the MAC addresses, configure the VM to appear connected to a printer. And you can see how tedious that can become. So it can be something that we can easily do, for example, using a script like VMware Cloak or VBox Cloak to help automate that process. And even in that situation, if all the techniques are addressed, minor architectural checks can still be made by the malware, as we'll see, that will determine whether or not we're actually running VM or not. So what's the name of the identifiable process used by malware to check if the machine is running inside a virtual box? And we have this at the top right here, which is the identifiable malware. It's the VBox service. There you go. So if it's running inside VirtualBox, it's most likely going to check for that process. What is the OUI automatically assigned specifically to VMware? So let's see if we can actually find the OUI to VMware. And this is MAC addresses, for example, VMs, okay, so what is the OUI for VMware? Let's see if we can find that. A simple Google query will show us that this is the OUI that's been assigned to VMware. So let's go ahead and get that. And I wonder if it's actually it's on the list that we had above. The 5056 is on this list. Yeah, this is actually the last one that's on this list. So that's the one assigned to VMware. Using Task Manager, what process indicates that the machine for this room is an Amazon EC2 virtual machine? So we're going to open Task Manager back up, and then we want to see what is the one. So I think it's Amazon SSM agent. That would be the background process, most likely, that will indicate that we're running on a virtual machine. Let's see if there's anything else that might be useful to us, but I think it's that first one, the Amazon SSM. Yeah, so I think it's the Amazon SSM agent.exe. So let me see if that is indeed the case. Amazon -SSM agent.exe. That is it. There you go. So that indicates that we are running an Amazon EC2 virtual machine. So now that we know that these are some of the techniques for VM detection, we need to look at a way that we can kind of bypass this. A version of checking for a VM or virtual machine is by looking at the temperature of the machine itself. So there's something called the Win32 temperature probe, and it's a WMI class that contains real-time temperature readings through the SM BIOS, the system management BIOS data structure. In a virtualized environment, the value will return not supported because typically virtual machines don't have that inside of the hardware, the basic input-output system. There are some other machines also that may return not supported because it doesn't necessarily exist on every single machine's SM BIOS feature. So just keep that part in mind. It doesn't necessarily mean that this thing is an actual virtual machine if it says not supported, okay? But there is a version of this that we can just test on our machine, which is basically the VM detection executable. I'm not going to run it because it's not going to do anything. We're going to open it in the debugger because we want to fix it and we want to patch it to make sure that we can actually get the result that we want. But essentially, when we run it without the patching, right, you just run it regularly, it's going to say proceeding with non-malicious activities. I guess I can run it because it shouldn't be that complicated to run. But basically, this is the code in the background that's going to check to see if there is some kind of a temperature probe on the virtual machine. And if there is, it's going to just say, hey, you know what? There we go. So proceeding with non-malicious activities because VM was detected, right? So that's basically what it says. And so this is the full code right here. If you, and the idea that they've given us is that you can compile it and run it on your physical machine to see how it changes its behavior, meaning I should run it on my actual laptop, which I'm not going to do. No actual malicious execution is inside the code, so it's safe to run. And the only thing that it's going to do is if it detects that it's on a physical machine, is that it's going to have this pop up. But I'm not going to run it because it would require that it would compile the code and run the code and do all that stuff. So I'm not trying to do all that. It's, I'm just going to take it for their on their word that this is going to happen. Plus, we're also going to change this, right? We're going to change it inside of the debugger that we just have right now, and then we're going to be able to see what it looks like inside of our virtual machine anyways, because as long as it gives us this response, that means that we've properly patched it and we've debugged it. So the architectural check, like checking temperatures, can be challenging. Fortunately, there are ways around this. For example, we learned that we can patch a function with NOPs to prevent it from executing, and we can do the same thing over here. So we'll be covering two other approaches: manipulating memory directly and changing the execution flow with EIP. So opening this again, go to the file, open this again, press F9 to start running, and then it will halt at the code that's marked as entry point. And then we're going to press Control G on the keyboard to bring up the enter expression to follow, and then enter this value, and it'll take us to the memory address. F2 to set up a breakpoint, and F9 to halt the execution. Now we're at the memory location here, and the block of instructions from this location corresponds to part of the C code snippet, the enumerator that will go ahead and essentially, I would say, probably enumerate what it would as far as the elements of the virtual machine, or the elements of the virtual machine that would help the malware detect whether or not it's actually on a virtual machine. So these are the comments that have been added to the right side to highlight the values to pass the function. And so let's just start with that element right there. So we'll just do these chunks of exercises. So this is fine. That's what the malware did. So I'm just going to go ahead and open the VM detection inside of our piece right here. There we go. So press F9 to start the running. Or I could just, let me see if F9 will actually work here. So if I press F9, no, it doesn't work. So I'm just going to do the forward button and it starts running. So now let's see. So it says debugging will halt at the point called entry point. And for me, it does not say that. So if I actually click on this, it says call VM detection, and that's all good. So if I run it again, or if I do, let's try run one more time. Maybe it'll do it and get to the entry point. Proceeding with non-malicious activities, VM detected. Okay, so that's actually running, and then it ended up closing itself. So I'm gonna run that one more time because it closed itself after it was done. It just did proceeding with non-malicious activities. So start running the program in the debugger. Debugging will halt at the code marked at the entry point. So press play, and it should stop at the entry point, but I don't see entry point on my screen right here. So maybe if we go to full screen so we can actually see the full piece. So I will exit split view right here. I will allow this. I will maximize this, and let's see if we can see entry point in here. Oh, we do. Okay, there you go. So there it is. So it was previously hidden, but it's right there. So it stopped at entry point. Excellent. So now what we can do is go and do the enter expression to follow, and enter this value to follow it, and then press F2 to set up a breakpoint at this memory location, then F9 to halt the execution. So what I need to do is, I wonder if Control G will work, right? Because hopefully it does. So if I do Control G, okay, there you go. That worked. Enter execution expression to follow. So I will paste that expression, and then there it is. So press OK. And so I have this now. So there we go. And then F2 to set up a breakpoint at this memory location. So we should be at the 10 E0, which is exactly where we are. And then breakpoint, I guess, is something that I want to do. So I should be pressing F2 to set up a breakpoint. But I wonder if this button right here, this breakpoint button, I wonder if that does the same thing. But I will try F2. And F2 does not do anything for me because it is just increasing my my display brightness on my computer. So I will need to find out how to set a breakpoint through the actual menu. So give me a quick second. Okay, so if we actually just right click on that item and go to breakpoint, F2 is toggle, I guess, so I can just click on that and it'll turn that piece into a breakpoint. So there you go. That's how we can do that. And then F9 wants to halt the execution here. And again, so halt the execution might be something that I don't know if I can do with my F buttons. So I need to see if there is a version of this that will allow me to do it. So let's see what I can do here. So as I anticipated previously, as I guessed, this button right here is the F9 button, because if we go to debug and then we look at what the value for run is, it is F9. So I'm just going to do that. And so I guess that would be our halt right there. So so we have now officially halted the execution right there. Now we're at the memory location. This and the block of instructions from this location corresponds to the part of the C code. To help us visualize this, there are comments on this. So presumably the comments would be something that I could actually see. And so let's see what the comments would be. You know, what is it? U return, WBM infinite, PM enumerator. So let me see if I can find any of those things. Okay, so there are no comments because I think the comments that he's referring to, the creator of the room, is comments that he added to the screenshot specifically. So these elements right here don't show up in the analysis that I'm making, but just looking at the data right here, these elements right here, I know that we're in the right space. So it says 10 E0 8D45E8 LEA-EAX, so 10 E0 8D45E8 LEA-EAX. So I know I'm in the right place. And then the next one is 10 E3, 10 E4, 10 E7, etc. And so 10 E3, E4, E7, etc. So I know we're in the right place. So now we're going to press F8 a few times to step through the code until you reach the memory location 10FD. And step through the code is accomplished by this button right here. So it says step into, and if we click on debug, we can actually see that as well. So step over, which says F8 right here. So that's technically it. So there we go. And then we want to get to which location? It says you want to get to the 10FD. So 4010FD, which is going to be down here. So we're just going to press this a few times until we get to that location, which is right there. So 4010FD, and that's the one that they're telling us to do right there. Here we can see that the value of EPB18 or uReturn is being compared to 0, and this goes to the C code, which if uReturn is 0. So this piece right here, we're trying to see if it actually compares to 0, and this is the part that I would love to actually see inside of the code right here. So what we can see right here is if it's comparing the EBP18 to 0. So I want to see if I can actually find that, to see if I can see EBP18 to 0, because that would be great. Unfortunately, because I don't have those comments, I can't see the stuff that he's talking about in this piece, where it's like if uReturn equals 0, because we can technically see it right here. But again, I don't have those actual comments for myself right here. So I am on this line, and then I do see the EBP18 comparing to 0. So this piece, CMP, DWord, etc., I'm assuming that is comparing the DWord variable, the global variable, to see if that this element equals to 18, and that's essentially it, right? So if it does, then it's going to do something, and if it doesn't, it's going to do something. So we want this if condition to evaluate to false. What we can do is edit the memory location pointed to by this so that it will contain the value of 1 instead of 0. And what did I just do here? I just shrunk out of that. So we want to change it so that it'll contain the value of 1 instead of 0. And to do this, we're going to right click on the line that has EBP18 and click follow in dump, then select EBP18. So right here on FD, we're going to right click it, and then we're going to follow and dump EBP18. So here it is, goodness gracious. And then we're going to do follow and dump and then address EBP18. And so let's see if that actually is the case. So when we do that, we'll see the bottom of the screen at the dump 1 window tab that the current memory location is FF08. So we have this right here. So in dump 1, let's make sure we're actually here. Okay, great. And so if that is indeed the case, the memory location should be at FF08. And I don't see a highlight. It does say that the dump is FF08. So that piece I see, but I don't see anything highlighted. Oh, I see. So FF08 would be the thing in the, yeah, so there it is. There it is. There's the actual highlight, and it's on FF08. Okay, great. Excellent. Double click on the rightmost 00 values. This will open up a modify value window. Enter 01 in the expression field and click the OK button. So on FF08, on the rightmost 00 values right here, so FF08, we see that on the rightmost 00 right there. We're going to double click on that, and it should bring this for me. There you go. It has the pop-up. And so what I want to do here is that put 01 in the expression field, which is right here, and then click the OK button. And it should change the value down here to 01, FF08. There you go. We have 01. Excellent. Very good. So to turn the attention back to the main window, CPU tab, press F8 a few times. You'll notice that the code will not exit anymore as it skips the execution from 1101 to 1100A. And what we've done is that we've manipulated the bits of memory location to direct da-da-da-da. However, the program will now crash if you continue running the program. And it was supposed to exit at the previous function, but we've introduced a bug since we intentionally skipped this. Don't worry, this always happens when messing around in debugger. So for us to continue to investigate, there's one other method that we can use that would allow us to jump around and continue. Okay, so I guess, so if I do this a few more times, yeah, so it skipped from this and it just went directly to this. And I would assume that that's not the ideal result because that's what we didn't want to happen. And last chance exception bug, etc. I keep getting the same thing at the bottom where it pauses it. So I guess it's not the ideal situation. So if we continue to run the program, it will crash. So if I press play, it would, yeah, it seems to not be working. So that is unfortunate for us because technically we want it to continue working, I guess. So the program was supposed to exit at the previous location, but we introduced a bug. Okay. This always happens when messing around. Okay. So for us to continue to investigate, there's one other method that we can use that would allow us to jump around. And let's say we want to skip everything and jump to this part of the code, this piece where it says thermal zone temperature, etc. in the assembly code. The instructions would be 401130 and 401139. So between those elements right here. So we want to get to the 401130 and 401139, which is right here. So this from here to 39. So these 4 lines right here is where we have this temporal zone temperature, that piece right there. Okay. So the great thing about debuggers is that we can change every value related to the program. We can change the values in the memory locations, the values on the stack, and even the values of the registers. The EIP register is the register that holds the memory address that tells the debugger what next instruction to execute next, and this can be edited. So going from the last step, on the registers panel on the right side of the screen, look for something that says EIP and then modify value. So this is what we have right here. And I think it's 40110A is what it's supposed to look like. So continuing from the last step, so 40110A, which is what I believe that is right here. And we're looking for the EIP value that says 40110A. So I need to go back, it seems. So let me see if I can actually do that. Okay, so to be able to achieve the rest of the stuff right here, because continue from the last step, I had skipped over this element. So we're supposed to end up at 40110A. So I literally restarted the program, or restarted this whole debugger by clicking this restart button right here. And I started from the very top of the instructions, meaning I came here and I first pressed play, right? Or pressed this part right here that I think it's like F8 or F9, there we go. So I pressed F9 and then it took me to the entry point. And then from here, I did the Control G to actually search for the expression, and then it took me to the element where I could set up the breakpoints. So this piece right here, and 4010E0, this piece right here. Then I clicked the right click and I put an entry point, or excuse me, a breakpoint, and then I did the play button one more time, or the F9 to halt the execution. And everything that you see right here is as it is. So this is what you see right here, right? So E0, that's where it started, and I got the execution. And I pressed this button, the step over, a few times until we got to 10FD. And then I right clicked on this, I went to follow and dump, and then I looked at the location, which took us down here to this portion, the F08, and then I changed this last value from 00 to 01. So literally repeated every step of this process, and now we have ended up at where we are right here. So right here, we have changed it to 01, and now we can press the F8 a few times so that we can move from 1101, and we can see that it is going to skip 1101 and end up at 110A, and this is where we want to stop. Okay, so we want to stop on 110A. That's where we are right now. So this is where I am, and so I want to stop right here, and essentially what we want to see is that it's going to skip this and it's going to end up here, right? So if I press this, let me make sure it's actually clicking. There we go. There it is. So it goes from there, and then it'll jump to 110A. So we see that it skips these other executions, and then it just stops at that location. So that's where we want to be for this next element to work. So it says we want to skip everything and jump to the part of the code that happens in the assembly code. This is where it's located, right? So from 110A, it would end up in this location where we have right here. So the great thing about it is that we can change the value, etc. So continuing from the last step, on the registers panel on the right side, we can see that EIP, and then we should be able to change that value. So you see that EIP right here is 110A, right? So now I'm actually here where the EIP value is 110A, and then this is what EIP is right here, the execution, right? The entry point or execution point, I think. So now what I want to do is I want to modify that value and enter this as the new value, which would be the line that this thing starts from. So it is this piece. I'm just going to copy this to make sure I don't make any kind of a mistake here. We're going to go here, modify the value, and then we're going to paste the expression, right? It says as the new value for the expression, I think. So it says modify value as the new value. I guess, yeah, that's what it is. So I'm going to paste that. Okay. And it takes me automatically to this location. Very good. Now we press F8 to step through the code. You'll notice that we'll jump directly to that instruction. Notice that the EIP marker now points to the location that we wanted. So, okay. F9 again would continue running the program, resulting in proceeding with malicious activities. And that would be the final piece of this. So this is where I'm at right here. And so this is the location as it says. So if I press play, let's see, it's running. So I guess there should be a pop-up that says, there we go, proceeding with malicious activities. So we did everything that we're supposed to do. Good job. You successfully prevented the malware from detecting that it was running. Okay, great. So in the C code snippet, what is the full WQL query used to get the temperature from that? So we want the C code entry. So let me just zoom out a little bit and go find the WQL query that's going to pull the temperature for us. And it's right here. So this is the execution query. this piece right here. So I think they want that full thing. If not, it might just be the select part. So let's see. Okay, that is not it. So to temperature from the Win32 temperature probe class. I'm pretty sure that was it, but I think they're looking for maybe this piece, the select from. I think that's the piece that they're looking for. So we'll go here and we'll try that again. Okay, great. There you go. That's the one. What register holds the memory address that tells the debugger what instruction to execute next? What register holds the memory address? I want to say, is that EIP? Yeah, that is it. So EIP is the piece right here. This thing that you see, that's the thing that tells what to execute next. Before U-turn is complete compared to 0, before U-turn is compared to 0, what is the memory location pointed by EBP04? So before it turns to 0, what is the memory location by 04, right? EBP04. Okay, in order to pull this off, the hint tells us that we need to run through the steps one more time. So I restarted the malware. I ended up at the entry point. I did Control G. I pasted the value that would take us to the location that we wanted. So Control G, and then pasting this value right here, and it took us to that address. And then I did the breakpoint. I did the F9 to halt the execution. And now we're at the E0, and we want to end up at this location. The 10FD is the location that they're talking about. So the function will da-da-da-da, and it will write value da-da-da-da. So what we're going to do is press F8 a few times to actually get to FD. So essentially what that means is just getting to this location again. So just going to press this until I get to FD. And there it is. So now the value is supposed to be EBP, right? So the location now, it says before U return is compared to 0, what is the memory location pointed to by EBP04? So if I right click this, I think this is where I can go and do the follow and dump, and then EBP, but that says EBP18. So EBP04, the memory value, that's the one that I think they want. So if I do follow and dump, there you go. So address EBP04, there it is. So this is the one that has EBP18 on FD, and then we want the one that's EBP04. So if I right click this and then follow and dump and do that, it should take me to that location, which is right here. So the FF1C, I want to say, is the value that they're looking for. So FF1C, it could also be the 10FA, so 004010FA. So let's try that, 004010FA. So that's not it. So the location then would be this piece right here. So 0019FF1C. So let's try that. So 0019FF1C. Yeah, that's the actual location. So we had to just right click on the one that says EBP04 and then do follow and dump EBP04, and then it will bring us to the bottom right here, and this is the one that they're talking about. All right, cool. So now we can talk about packers, and we'll do an overview of packers, and then we'll go through identifying and unpacking, and then we will be officially done. Obfuscation is a technique that aims to intentionally obscure data, right? So to disguise data, to make it undecipherable by the naked eye, and it's harder to understand or analyze. So the most common obfuscation technique is using encoding techniques. So command line strings or domain names is encoded using popular encoding techniques like XOR or base64. And when you see something like this, right, that's basically a base64 string. So let's see what this actually means by going to our favorite tool, which is CyberChef, and then basically you just drop in whatever the input is, and then usually you can automatically detect it. And so in this particular case, it did not automatically detect it. So from base64 would be my recipe. And then this is the response. This is a base64 encoded string. That's basically all it says. So nothing fancy. So using encryption techniques, this involves encrypting data such as communications to a command and control server, file formats, and network traffic. The most common types are symmetric key and public key key encryption. Symmetric is private key, public key is asymmetric. So these are encryption techniques that would encrypt the strings and the value so that you can't even decipher it. So this is encoding, and as you saw, it's very easy to decode encoded string, not so easy to decrypt encrypted strings. And code obfuscation involves various techniques like manipulating the code to alter the syntax and structure, renaming functions, splitting code across multiple files or segments, and there's a lot that can be done. So we don't go really crazy in this particular video. We just want to know about the wide use of packers in malware, and that technique can be considered to fall under obfuscation. So packers are tools that compress and encrypt executable files. It compresses the target executable and embeds it within a new executable file that serves as a wrapper or container. This dramatically reduces the size of the file, making it ideal for easy distribution and installation. Also, it has code obfuscation, runtime packing, and anti-debugging techniques. And because of these features, they are a popular tool for malware authors. So there are a lot of packers available. These are the list of them. Each of them are unique and they can have different algorithm for packing. And these are some of the most common ones that have been outlined here. If you're actually inside of this room, you can literally click on any of these and it'll just take you to the given website for it. So for example, this is the website for AutoHotkey, and you can go and I guess it's called Impress, but the website itself was AutoHotkey. Themida, VM Protect, all these things could be packers. If you don't have access to this room, you can just Google these names and you'll be able to find the websites. So not all programs are malicious because, as we just talked about, it can just condense or compress the program to make it easier to transfer and easier to use. So protecting the intellectual property from theft is one of the big things as well when you do something like packing, because you don't want the source code to be exposed. And Themida is widely used to prevent video game cheating. It's one of the packers that's available. So packers encrypt and obfuscate a program. It would be impossible to know that malware capabilities without actually running the type of malware that has been packed. Because of this, we can't reliably depend on static analysis and signature-based detection to determine the capabilities. The only thing that we can glean from malware sample at this state is the packer tool that was used, meaning when it's packed and you're doing static analysis, the only thing that you can really learn about the malware, is what packer tool was actually used. And it's a good starting point because we'll be able to kind of figure out what that packer does to be able to decipher it. So what is this base 64 encoded string? So we already have our CyberChef running, so we will just go ahead and do that. I mean, it literally says the same thing. So this is a base 64 encoded string. Was that? Oh no, the other one said this is n base 64 encoded string. This one says this is a base 64 encoded string. Okay, so identifying and unpacking. Let's get into it. So we have a packed malware piece that is on our virtual machine. We can use it inside of Detected Easy, also known as DIE, and it'll show us the identification. So if it's actually been packed, it'll display it as best guess under this section. And so from this particular screenshot, I want to say that this is the element, the Microsoft Linker, Visual Studio, etc., under the best guess right here, the packer, or excuse me, the packer here, my bad. So packer is UPX, there you go. And the linker is Microsoft Linker, but the packer itself is UPX, as we can see. So we can also click on the entropy button on the right side of the screen to open the entropy window. The entropy window looks and determines how much entropy each section has. As you can see, it has been determined that section 1 is packed, as we can see that right here. Excellent. So entropy measures the level of disorder or uncertainty in a system. Packed malware tends to have high entropy due to the randomness of the packing process. Another tool is PE Studio, which lists information on PE files. It's important because there are specific packers that will still leave clues. We can click on PE Studio, go to the menu and open it. On the list of items on the left panel, click on Sections Self-Modifying. So let's go here. I already have PE Studio open, so I can do File, and I can open the file, and then open up the packed malware that we have here. And it says, where is it? It's on the list of the items on the left. We have the Sections Self-Modifying. that can bring our element to us. So there we go. I have section self-modifying. There we go. And so it has UPX0, UPX1, and UPX2. And I do know that we need the value of entropy for UPX2 for one of our questions. So it's 2.006. That's one of the answers that we need. And then the other question at the bottom asked for the Microsoft version, which is 14.16. So that one is available here. So where is it? Right here. So 14.16 is the Microsoft linker. And the P Studio, what's the entropy of UPX2? And we have 2.006, 2.006, and that's that answer. And that's basically all the questions that we have for this section, but we're going to read through everything else as well. So what do we have here? We have the section names of standard PE file are text, data, resources, but in the output above, we can see that this section names have been changed. The strings PX1, PX0, 1, and 2 are some of those identifiable pieces of information that packers like UPX leave behind. Not all packers change this value, but usually this is the most accessible first place to look. Because different packer tools use various methodologies in packing executables, sometimes tools like Detected Easy could not identify all types of packers. So we can do automated unpacking. Once the packer for packed malware is identified, it's possible to see an unpacker, to use an unpacker to get the original file. Some are readily available, like in the case of UPX, where you can use the same packing program for unpacking. For other commercial tools like Thermita, you might have to rely on unpacker scripts made by third parties. These are some of the scripts. If you chance upon malware packed with an obscure tool or modified to thwart available scripts, things might get more difficult. There are services like UnpackMe, where you can upload a sample and it will try to identify and unpack the malware for you using custom unpacking and artifact extraction. This is still not perfect. So this is UnpackMe, available at unpack.me, and you would sign up and you would upload your malware sample. Manual unpacking and dumping is probably the best way to execute it and then try to unpack it. So when a packed malware is executed, the wrapper or container code performs decryption and deobfuscation. Once fully unpacked, the malware can proceed. At this point, the packer is useless, and we can thoroughly analyze the malware by debugging it using a debugger. So we can use our X32DBG and continue with this. So packed exe, I'm going to open it and do Control G, and then we're going to jump to this spot. So I already have, let me see, where is it? It's right here. No, that's Task Manager. Where's DBG? There's DBG. Great. So we're going to open our packed exe right here, and then we're going to click G and just go to that element. So G, and then we're going to go to that location, press OK, and it'll take us automatically there. Now we're at this location. This is before the entry point. So press F2 to set a breakpoint, then F9 twice to move execution to this location. So we're going to go right here, and we're going to do right click, breakpoint, because I don't have F2 really accessible, and then I'm going to press F9 once, F9 twice, and now I'm at that specific breakpoint, which is the 2D4 element. Great. So now we have jump packed, and that is it. Jump packed. There you go. So press F7 to jump to the memory location 401262. This location is the starting location of the legitimate program, and so we're going to go right here, and under debug we're looking for the F7 option, which is step into. So I will press that, and it will take me to the call packed location. Very good. So 262 is what we're looking for. There we go, 262. By now you may be curious about the memory location 2D4 and 262 and their relevance to what we're doing. When this UPX packed malware is executed and the execution location reaches this, the 2D4, it indicates that the legitimate part of the program has already been successfully unpacked and is now copied in memory 401262. As outlined in the next steps, we can now begin dumping from this location. Other packers have different approaches to unpacking, so the steps above would not work for them. To start dumping, go to the top bar menu, click Plugins and Sila. So we're going to do Plugins and we're going to do Sila. I think that's how you pronounce it. It's a tool that dump process memory to disk and fix and rebuild the import address table. We'll use this to unpack legitimate parts of the program, so it will have updated memory locations. Once the Sila plugin is open, click the dump button. So we'll just click dump. Where is it? Right there, dump button. And then we're just gonna, I guess, save it. So I'll just do the save in the malware location. There it is. There you go. To the exact location as the original file. Okay, so that's good. If you try to run this, an error will appear. This is because we have not fixed the import address table yet. So back in Sila, click the IAT auto search button to start. This scans the memory of the process to locate it. So we're going to do IAT auto search. Result of the da-da-da is different. Do you want to use ISH? Yes, I do want to do it. And so IAT was found. Oh, let me make sure that my machine does not expire on me, because that would really suck. So we're going to add an hour to our machine. Hopefully that will be fine. All right, so where are we? We are here, right here. Okay, great. So if you try to run it, this is what happens. Back in Sila, we're going to click auto search. This scans the memory to import the address table. If a pop-up asks you if you want to use it, click, oh, I see. If a pop-up window asks if you want to use AAT, select no, then press OK. And I clicked yes, so there's the IAT. So let me do auto search one more time, and then no, and then OK. I guess I'm not sure if I did that wrong. At this point, the appropriate values are related to the IAT are now computed. We can now click on the Get Imports button to this selection. I wonder if I actually did this wrong or right. So I will now do Get Imports, and we should have these values. So user DLL, okay, D00, D108, and D110. Let's see if that's what we got. D00, 108, and 110. Okay, that seems right. The list will show all the DLLs. This is short because the program is simple, and actual malware will have a longer list. Sila will find invalid entries. This is marked with the X icon next to it, so we can see that right there. To delete these, go to through each invalid entry, right-click, and select Cut Thunk. Once deleted, you should be left with valid entries with checkmark icons. Click on the Fix Dump button, then select the previously generated dump file, and a new file will be created in the same directory as the dump file with the SCY appended to its file name. If you execute this, the program will now work correctly. So first, let's go and see if we need to remove anything here. So both of these are done. So we're just going to, what is it? I'm going to click on this, right? And then we're going to do, where's the, not, I guess if I right click on it, it says cut thunk, but it's not there. So if I'll right click, I see. So I have to right click on the individual ones, and then we cut thunk. Okay, great. So there you go. So now we have cut the thunks. That's so funny. And so since we've done that, we can do fix dump. So now we're going to click on fix dump. There you go. And so I have this now. A new file will be created in the same directory as the dump file with the string appended to its file name. So I don't have anything. Oh, I see. I need to do select the previously generated dump file. So this is my previously generated dump file. Open that. And once I do that, a new file will be created in the same directory. I guess there's already a file created. Yeah, there you go. So dump SCY, it's already there. Okay, so great. So now it says if you executed this, the program will now work correctly. You can confirm it if the unpacking was successful by inspecting the generated file using PE Studio or Detected Easy. Here's the output of Detected Easy. You'll notice that it's not packed anymore. So let me see if I can just click on this and see if I can use Detected Easy, because it said I could just right click it and open Detected Easy. There you go. So Detected Easy was one of the options. So it'll open, and I guess yeah, so there's no packer or best guess or whatever. It just says compiler, Microsoft Visual C+, and linker, which is that. So that is all good, and same thing that we have over here. And we already have the answers to these questions, and we are officially wrapped. So as a conclusion, as a final thought here, we did anti-debugging, we did VM detection, and we looked at packers. And I will say that I don't think that these are the fully inclusive, like all-inclusive list of everything that is done with anti-debugging, right? So, or anti-reverse engineering, I should say. I don't think these are all of the tactics, because hackers are constantly working and they're constantly learning and they're constantly developing new methods to do this. So this was just kind of an introduction to anti-reverse engineering. We used PE Studio, we used the DBG32, we also looked at DIE, Detected Easy. So these were some of the tools that we used. We looked at a few different approaches to anti-reverse engineering, and hopefully it sheds a little bit of light for you and you kind of understand what the process is like and what can be done. This is not the be-all and end-all of this particular education. Very similar to everything else on this channel. So most of the stuff that we've done is an introduction to things, and it's up to you to dig deeper into it if it's something that interests you, right? There is a handful of playlists, for example, the CompTIA Security Plus, Network Plus, Linux Plus, and then I'm going through Pentest Plus. Like those things, I would say, are pretty comprehensive as far as those categories are concerned. But even within Linux Plus or within Pentest Plus, as we're going through it, there are so many tools that are introduced during those studies, and we don't specialize in any of the tools. We say, hey, this is the tool, this is what it does, this is what you can do with it, here are some examples of what you can do with it, and then we move on to the next one. Probably the one where I did like the most in-depth introduction or in-depth overview of it was the packet tracer from Cisco when we were doing Network Plus. But even with that, there are so many other things that you can do with the packet tracer that it would just take an entire course to try to teach you just that one software. It would take hours upon hours, dozens of hours, to try to share with you what exactly you can do with that one software. So all of these things need to be considered as you're looking at everything that we're going through, including anti-reverse engineering. We did one module on malware analysis, but this does not mean that you are now a malware analysis expert. And the only thing that we're going to be doing after this is done is going and looking at an actual exercise where we run malware analysis on something. So we're no longer going to be talking about any ideas or strategies for doing malware analysis. We're just going to implement everything that we've learned so far so that we can go ahead and get those final points and wrap up the SOC level 2 pathway that's inside of TryHackMe. But that, I mean, for the most part though, like considering everything, considering all the different resources, this was a great security education where we went through SOC level 1, we did CYSA plus, we did all those things, and now we have finished SOC level 2. So I can tell you from my own personal experience, I feel much more competent than I did a year ago when I started all of this stuff, right? So just, take it with a grain of salt. I think there's a lot of other things that can be learned. We can always learn more, we can always practice more and advance more. And I encourage you to do that. I encourage you to do independent study and download some of these tools or download the virtual machines and do some of these exercises just so you can really understand what's going on instead of just watching videos and following along click by click. You won't learn everything that you need to learn by simply just doing that. So that's my 2 cents on it. If you found this video useful and if you've gotten any value from this channel, I do encourage you to like, subscribe, and turn on that notification bell so that you get notified the next time that a video comes out, because we are constantly uploading videos. We are at 355 videos as it stands right now. I have some really popular ones that are on the home page here. We have the created playlists, we have members only videos, we have and these are reserved for Hackaholics Anonymous, and you'll find out how you can join Hackaholics Anonymous if you want to. SOC level 1, SOC level 2, security engineering, and then there's these individual ones that are pretty popular. So CompTIA Pentest Plus right now is what we're working on right now. This is the 2025 version of the Pentest Plus. Network Plus is already done, and this is the 2025 version of Network Plus. Python for Hackaholics Anonymous, CompTIA Security Plus examination, Linux Plus exam prep, Cybersecurity 101. These are some of the most popular playlists that I have right now. Linux Plus is very, very popular. A lot of people are using it. I think Network Plus is probably the next one that was like really popular. And again, there's just more stuff that's going to be coming out. There's going to be CompTIA CYSA Plus that's going to come out. There's going to be AI for cybersecurity, where we learn how to program AI, essentially how to train AI to create our own security analysts, our own automated security engineer agents, excuse me. So there's a lot of stuff. We're not going to be slowing down on content anytime soon on this particular channel. And if you're interested in anything with cybersecurity, ethical hacking, pen testing, or system administration, because this is also kind of goes into system administration. If you're interested in any of this stuff, then you definitely want to be a member of this community, and I think you will get a lot out of it. So if you haven't done so already, make sure that you like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel. If you're serious about your CySec education and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the supporter, agent, guardian, and master. Each tier gets their own Discord server and early access to content. The agent, guardian, and master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. I hope I see you in the Discord chats. If not, I hope I see you in the comment section. And then that is it for today. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker/protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease. And I'll see you in the next video. Later.